Welcome everyone. Today we are going to talk about something that sounds very fancy but is actually a beautifully simple idea, the principle of inclusion-exclusion. The full name might feel a little intimidating at first, but do not worry. By the end of our time together, you will feel completely comfortable with it. In fact, I think you will find it surprisingly elegant. What we are really doing today is answering one very natural question. When we have a collection of groups, and some things belong to more than one group at the same time, how do we count the total number of distinct things without accidentally counting the same thing twice? And the way we are going to approach this, the specific lens we will use throughout our entire discussion, is something I am calling tracing the state of the count. That phrase is going to become your best friend today. So let us get started. The setup. Before we dive into any formulas, I want to make sure we are all looking at the world in the same way. Throughout this lesson, we are going to represent finite sets. That is, collections of things with a definite, countable size, as circular regions. Think of each circle as a bubble holding a group of elements. Simple enough, right? Now here is an important agreement I want us to make about how we read these diagrams. When you look at the picture and you see one of those small, distinct inner regions, the smallest compartments the circles create by overlapping, you should think of that region as representing exactly one element. Just one single thing sitting there. I want to be upfront with you. Mathematically speaking, any region could contain 0 elements, or 1, or 100. But for the purpose of building our intuition visually, each small region in our pictures will represent exactly one element. This is our teaching agreement, and it will make everything much cleaner to understand. Now, the most important idea I want you to carry through this entire lesson is the concept of the count state. Here is what count state means. At any point as we build our formula, step by step, we are going to ask ourselves, how many times has this particular element been counted so far? That number, that running tally for a single element, is its count state. If an element has been counted once, its count state is 1. If it has been counted twice, perhaps because it belongs to 2 groups and we added both groups, its count state is 2. If it has somehow vanished from our count entirely, its count state is 0. Our entire goal, the whole mission of this lesson, is to arrive at a mathematical formula where every single element in the union of our sets has a count state of exactly 1. Not 0, not 2, not 3. Exactly 1. Every element, counted exactly once. That is the prize we are working toward. Case n equals 2, tracking the count state. All right, let us start with the simplest possible case. Just 2 sets. Let us call them A and B. We want to find the total number of elements in the union of A and B, meaning the total count of all the distinct things that belong to A, or to B, or to both. What is the most natural first instinct? You might say, well, just add them. Take the size of A and add the size of B. Simple. And that is exactly what we do first. We write the size of A plus the size of B. Now, let us look at what happens to each element under this first step. Imagine our 2 circles, the A circle on the left and the B circle on the right. They overlap in the middle, creating 3 distinct regions. There is the part of A that does not overlap with B. There is the overlap in the center. And there is the part of B that does not overlap with A. Consider an element that lives strictly on the left side, only inside A and not in B at all. When we count the size of A, this element gets counted once. When we count the size of B, it is not there, so it is not counted again. Its count state is 1. Perfect. That is exactly where we want it. Now consider an element that lives strictly on the right side, only inside B and not in A. By the same reasoning, when we count the size of A, it is not there. But when we count the size of B, it gets counted once. Its count state is also 1. Wonderful. But now look at the element sitting right in the middle, in the region where A and B overlap, the intersection. When we count the size of A, this element is inside A, so it gets counted. That is count state 1. Then when we count the size of B, this element is also inside B, so it gets counted again. That brings it to count state 2. 2. And we only want 1. So if we naively write the size of A plus the size of B, the elements purely in A sit at count state 1, the elements purely in B sit at count state 1, those are fine. But the elements trapped in the intersection sit at count state 2. They have been counted twice, and that is a problem we need to fix. Case n equals 2, the correction step. So how do we fix that double-counted center element? It is almost embarrassingly simple. We just subtract the intersection once. Our formula becomes the size of A plus the size of B minus the size of A intersect B. Let us trace what this does to each region. The elements that live only in A, they are still at count state 1. Subtracting the intersection does not touch them, because they were never in the intersection to begin with. They remain at 1. Good. The elements that live only in B, same story. They are still at count state 1. The subtraction does not affect them either. Still good. Now look at that center element, the one that was causing trouble. It started at count state 2 after the first step. And now we subtract the size of A intersect B, and this center element lives inside A intersect B, so it gets subtracted once. 2 minus 1 equals 1. Its count state is now exactly 1. It has been brought back in line. Every single region in our picture now reads a count state of 1. The outer left region, 1. The center, 1. The outer right region, 1. The formula, the size of A plus the size of B minus the size of A intersect B, gives us the perfect, exact count of every distinct element in the union of A and B. Nothing is missed, nothing is double counted. And that one subtraction step, that minus the intersection, is the heart of what inclusion-exclusion means. We included too much, so we excluded the excess. Inclusion, then exclusion. Beautiful. Explicit set example, n equals 2. Now, I know that circle diagrams and abstract reasoning are helpful, but sometimes you really want to see actual numbers. Actual elements you can point to and say, yes, that one, right there. So let us do exactly that. Let us define two very concrete sets. Set A contains the elements 1, 2, 3, 4, and 5. Its size is 5. Set B contains the elements 4, 5, 6, and 7. Its size is 4. Now, here is the question. What happens if we just blindly combine them? If we dump all the elements of A and all the elements of B into one big pile without thinking? We would write out 1, 2, 3, 4, 5. That is 5 entries from A, and then 4, 5, 6, 7. That is 4 more entries from B. That gives us 9 entries in total. But wait, look carefully at that list. The element 4 appears in it twice, once from A and once from B. And the element 5 appears twice as well, once from A and once from B. Both of those elements have a count state of 2. They have been counted twice, even though each of them is just one single thing. So our raw addition gives us 9, but there are not actually 9 distinct things here. There are duplicates hiding in there. You can see this clearly if you look at the Venn diagram. On the left side, you have the elements 1, 2, and 3. They belong only to A. On the right side, you have 6 and 7. They belong only to B. And right in the middle, sitting in the overlap, are the elements 4 and 5. They belong to both A and B simultaneously. Those middle elements, 4 and 5, are the troublemakers. They are the ones with a count state of 2 after our naive addition. And our next step will fix that. Correcting the explicit sets. All right, so we know the problem. Elements 4 and 5 have each been counted twice, giving us a raw total of 9, when the true answer should be smaller. Let us now apply the fix. We need to find the intersection of A and B, the explicit list of elements that live in both sets at the same time. A contains 1, 2, 3, 4, 5. B contains 4, 5, 6, 7. Which elements appear in both lists? Look carefully. It is 4 and 5. So the intersection of A and B is the set containing 4 and 5. Its size is 2. Now we apply our formula. The size of A plus the size of B minus the size of A intersect B. Plugging in the numbers, 5 plus 4 minus 2. 5 plus 4 is 9. 9 minus 2 is 7. 7. That is our answer. But let us not just trust the arithmetic. Let us verify it by listing every element in the union of A and B ourselves, by hand. A union B contains 1, 2, 3. Those come from A only. Then 4 and 5. Those are in both, but we only write them once. Then 6 and 7. Those come from B only. So the true combined set is 1, 2, 3, 4, 5, 6, 7. Count them one by one. 1, 2, 3, 4, 5, 6, 7. That is 7 elements. Exactly what our formula gave us. This is the principle of inclusion-exclusion working perfectly on real, explicit numbers. The formula is not magic. It is a precise, mechanical correction. We included too much by adding naively, and then we excluded the excess by subtracting the intersection. The result is a perfect count. Now, 2 sets is a great starting point. But what happens when things get more interesting? What if we have 3 sets? Let us find out. Case n equals 3, the first sum. Now we move up to 3 sets. Let us call them A, B, and C. We want to count the total number of distinct elements in the union of all three, every element that belongs to A, or to B, or to C, or to any combination of them. And just like before, we start by asking, what is the most natural first step? We add the sizes of all three sets individually. The size of A, plus the size of B, plus the size of C. Now let us carefully trace the count state of every region in our Venn diagram, and with 3 circles, we have quite a few regions to think about. Picture 3 circles, A on the upper left, B on the upper right, and C at the bottom. They all overlap with each other, creating a total of 7 distinct regions. There is the region belonging only to A, the region belonging only to B, the region belonging only to C. Then, there are 3 regions where exactly 2 circles overlap. The region in A and B but not C, the region in A and C but not B, and the region in B and C but not A. And finally, right at the very center, there is the region where all 3 circles overlap at the same time. So, after step 1, after adding the sizes of all 3 sets, what is the count state of each region? The element that lives only in A gets counted when we add the size of A. It does not get counted for B or C. Its count state is 1. Fine. The element that lives only in B, count state 1. The element that lives only in C, count state 1. All 3 outer-only elements are sitting safely at 1. Now look at the region where A and B overlap, but C does not reach. The element there gets counted when we add A, and counted again when we add B. Its count state is 2. Similarly, the region where A and C overlap, but not B, count state 2. And the region where B and C overlap, but not A, also count state 2. All 3 pairwise overlap regions sit at count state 2. They have each been counted twice, and we need to bring them down to 1. But now look at the very center, the region where all 3 circles meet simultaneously. When we add the size of A, this center element is inside A, so it gets counted. Count state 1. When we add the size of B, this center element is inside B too, so it gets counted again. Count state 2. When we add the size of C, this center element is inside C as well. Count state 3. 3. The very center element has been counted 3 times. We have got both overcounting at the pairs and serious overcounting at the center. Time to start trimming. Case n equals 3, trimming the pairs. Step 2. We subtract the pairwise intersections. We subtract the size of A intersect B, then subtract the size of A intersect C, and then subtract the size of B intersect C. Let us trace through every region again and see what these subtractions do to the count state. The element that lives only in A, it is not in any of those pairwise intersections, so none of the subtractions touch it. It stays at count state 1. Good. Same for the elements living only in B and only in C. They are not in any pairwise intersection, so they remain untouched at count state 1. Now look at the region where A and B overlap, but C does not reach. That element was at count state 2. When we subtract the size of A intersect B, this element lives inside A intersect B, so it gets subtracted once. 2 minus 1 equals 1. Its count state is now 1. Perfect. Similarly, the element in the region where A and C overlap but not B was at count state 2. When we subtract A intersect C, it gets knocked down by 1. 2 minus 1 equals 1. Count state 1. And the element in the B and C overlap region was at 2. Subtracting B intersect C brings it to 1 as well. All 3 pairwise regions have been successfully corrected to count state 1. Excellent. That looks like progress. But now we need to check on the center. The center element started at count state 3 after step 1. What do the 3 subtractions do to it? The center element lives inside A intersect B. So when we subtract A intersect B, the center element is included in that subtraction. Its count state drops from 3 to 2. The center element also lives inside A intersect C, so when we subtract A intersect C, it gets hit again. Count state drops from 2 to 1. And the center element lives inside B intersect C as well, so when we subtract B intersect C, it gets hit a 3rd time. Count state drops from 1 to 0. 0. The center element has completely vanished from our count. We overcorrected. By subtracting the 3 pairwise intersections, we accidentally subtracted the center element 3 times in total. 3 minus 3 equals 0. It disappeared entirely. So now we have a new problem. The pairwise regions are correct. They are all at count state 1. But the center is broken. It is at count state 0, as if that element does not exist at all. We need one more step to rescue it. Case n equals 3. The final state. Step 3. We add back the triple intersection. The size of A intersect B intersect C. Just one more term added back in. And this single addition is the precise fix that makes everything right. Let us check every region one final time. The element that lives only in A, it is not in A intersect B intersect C, so adding that term does not affect it. It remains at count state 1. Good. The elements living only in B and only in C, same reasoning, not affected. Still at count state 1. Good. The element in the region where only A and B overlap, not C, it is not in the full triple intersection either, because it is not in C. So adding A intersect B intersect C does not change it. It stays at count state 1. Good. And the same is true for the A and C only overlap region and the B and C only overlap region. None of them are in the triple intersection, so none of them are affected. They all remain at count state 1. Now the center. The center element was sitting at count state 0, completely erased. But the center element lives inside A intersect B intersect C. It is the very element that triple intersection is describing. So when we add the size of A intersect B intersect C, the center element gets added back exactly once. 0 plus 1 equals 1. Count state 1. The center is restored. Look at the full picture now. Every region, every single one, sits at count state 1. The 3 outer-only regions, 1. The 3 pairwise overlap regions, 1. And the very center, 1. And the complete formula for 3 sets is the size of A plus the size of B plus the size of C, then subtract the size of A intersect B, subtract the size of A intersect C, subtract the size of B intersect C, and finally add back the size of A intersect B intersect C. Add the singles. Subtract the pairs. Add back the triple. That alternating pattern, add, subtract, add, is not an accident. It is the heartbeat of inclusion-exclusion, and we are about to see it pulse even further when we move to 4 sets. But first, let us make sure this formula works on real, explicit numbers. Explicit set example, n equals 3. Let us take 3 very concrete sets and trace through the entire 3-step process element by element. Set A contains the elements 1, 2, 3, and 4. Its size is 4. Set B contains the elements 3, 4, 5, and 6. Its size is 4. Set C contains the elements 2, 4, 6, and 8. Its size is 4. Now I want you to pick one specific element and follow its journey through every step. The element we are going to track is the number 4. Why 4? Because 4 appears in all 3 sets at the same time. It is in A, it is in B, and it is in C. It is the most interesting element, the one sitting right at the very center of our Venn diagram in the region where all 3 circles converge. In the diagram, you can see the arrangement clearly. The element 1 lives only in A, on the far left. The element 5 lives only in B, on the far right. The element 8 lives only in C, at the bottom. The elements 3 and 6 are each shared between 2 of the sets, and the number 4 sits right at the center, claimed by all 3 simultaneously. All right, step 1. We add the individual set sizes, 4 plus 4 plus 4. That equals 12. Now think about what happened to element 4 specifically. It was counted when we added the size of A, count state 1. It was counted again when we added the size of B, count state 2. And it was counted a third time when we added the size of C, count state 3. Right now, the number 4 has a count state of 3. It has been counted 3 times, even though it is just one single element. We are already 12 total, but the true answer will be much smaller. Let us move on to step 2 and start correcting things. Trimming the explicit n equals 3 sets. All right, we left off with a raw total of 12, and we know that element 4 has been overcounted 3 times. Time for step 2. We subtract the pairwise intersections. We need to find the 3 pairwise intersections explicitly, meaning we list the actual elements that 2 specific sets share. First, let us find the intersection of A and B. A contains 1, 2, 3, 4. B contains 3, 4, 5, 6. Which elements appear in both? 3 and 4. So the intersection of A and B is the set containing 3 and 4. Its size is 2. Next, the intersection of A and C. A contains 1, 2, 3, 4. C contains 2, 4, 6, 8. Which elements appear in both? 2 and 4. So the intersection of A and C is the set containing 2 and 4. Its size is also 2. Finally, the intersection of B and C. B contains 3, 4, 5, 6. C contains 2, 4, 6, 8. Which elements appear in both? 4 and 6. So the intersection of B and C is the set containing 4 and 6. Its size is again 2. Now we subtract all three of those pair sizes from our running total of 12. 12 minus 2 minus 2 minus 2. That is 12 minus 6, which equals 6. Our running total is now 6. But here is the critical question. What happened to our tracked element, the number 4? Let us trace it very carefully through each of those three subtractions. When we subtract the size of A intersect B, which is the set containing 3 and 4, the element 4 is inside that intersection, so 4 gets subtracted. Its count state drops from 3 to 2. When we subtract the size of A intersect C, which is the set containing 2 and 4, the element 4 is inside that intersection as well. 4 gets subtracted again. Its count state drops from 2 to 1. And when we subtract the size of B intersect C, which is the set containing 4 and 6, the element 4 is inside that intersection too. 4 gets subtracted a third time. Its count state drops from 1 to 0. 0. The number 4, which is a perfectly real element sitting right in the center of all three sets, has been completely erased from our count. It has been subtracted once for each pairwise intersection it belongs to, and since it belongs to all three pairwise intersections, it was hit by all three subtractions. 3 minus 3 equals 0. It vanished entirely. Our running total of 6 is still wrong because element 4 is not being counted at all. We need to rescue it, and that is exactly what step 3 is for. The final state of the set, step 3. We add back the triple intersection, the set of elements that belong to all three of A, B, and C simultaneously. So let us find it. A contains 1, 2, 3, 4. B contains 3, 4, 5, 6. C contains 2, 4, 6, 8. Which single element appears in all three lists at the same time? Just 4. Only 4 is a member of A and B and C all at once. So the intersection of A, B, and C is the set containing just the element 4. Its size is 1. We add that to our running total. 6 plus 1 equals 7. And look at what this does for element 4. Its count state was sitting at 0, completely missing. Adding the triple intersection adds it back exactly once. 0 plus 1 equals 1. Element 4 is restored. Its count state is now 1. Let us now write out the complete arithmetic from start to finish, so you can see the whole chain in one breath. 4 plus 4 plus 4. That is the sum of the individual set sizes. Minus 2, minus 2, minus 2. Those are the three pairwise intersection sizes being subtracted. Plus 1. That is the triple intersection being added back. 4 plus 4 plus 4 is 12. 12 minus 2 minus 2 minus 2 is 6. 6 plus 1 is 7. 7. That is our final answer for the size of the union of A, B, and C. Now let us verify it by building the union by hand. The union of A, B, and C contains every element that appears in at least one of the three sets, listed once and only once. Going through all three sets and collecting every unique element, 1, 2, 3, 4, 5, 6, and 8. Notice that 7 is not here. None of our three sets contain 7, and we list each element only once, even if it appeared in multiple sets. Count them. 1, 2, 3, 4, 5, 6, 8. That is 7 elements. Our formula gave us 7. Our manual count gives us 7. They match perfectly. The principle of inclusion-exclusion, applied step by step, gives the exact right answer, and now we understand precisely why. Every element in the union has been brought to a count state of exactly 1, through a careful alternation of additions and subtractions.